Hello students. So in today's class we are discussing about the expression for impedance and current in LCR series circuit using a J operator. This question is from alternating current topic. So if you see the question, they have asked you the impedance and even the current equation. First we will see the how to derive the impedance equation by using the LCR series and J operator. Then we are going to discuss the expression for current in the LCR series circuit by using a J operator. So this is our circuit where you can see so we are using a resistor, capacitor and inductor. Already we know the work of the resistor, the function of the capacitor and the inductor. In the first step, we need to write the expression for resistance impedance. So the resistance impedance here is, this is ZR and here we are taking it as a ZC and here we are taking it as a ZL. Okay. So if you write the expression for resistance impedance, that is ZR equal to R, and then inductor impedance is ZL equal to J into omega into L. This is the previous equation where we are derived the impedance equation in terms of the inductor, and capacitor in terms of capacitor impedance in terms of J operator, that is 1 divided by J into omega C, where we already know that by mathematically, 1 by J can be written as minus J, because if I take this J to the numerator it will be minus. Okay. Or standard equation, that is 1 by I equal to, we always write it as minus I. So in the place of I we have a J, just replace. So I by J we can write it as a minus J. Fine. Next, so in our third equation, let's put 1 by J value as a minus J. The expression will be therefore ZC equal to minus J divided by omega into C. Okay. So next, if we want the total impedance of a series LCR is Z equal to sum of all this. So resistance, capacitor, inductor, impedance. So those are ZR plus ZL plus ZC. Okay. So already we derived the expression for a ZR, ZL and ZC. So write all the things in the total impedance value. So from these two, second and third equation or expression, we can take the J as a common. So taking J as a common, it will be J equal to R plus J into omega L minus 1 divided by omega C. So this is our final expression for impedance. In the examination, you can write up to this much. That is enough. If you want to derive the expression for magnitude of that impedance, that will be modulus of Z equal to square root of R square plus omega L minus 1 divided by omega C whole square. So this is all about the, at last omega L, we already know that in terms of reactance you can write as a XL and reactance of a capacitor will be XC. I hope the expression for impedance was clear. So next we'll derive the expression for current. So next, for a current expression, so we need to consider the Ohm's law in a AC circuit, that is I equal to V by Z. Why we are taking a Z? We can take it as R, but we already know that so in our LCR circuit we are concentrating on the impedance. Okay, so that impedance, that is Z. So we already know that the impedance nothing but it is also opposition to flow of a current. It work as same as of our resistance. Okay, I equal to V divided by Z. So substituting the impedance, so already we have derived in previous one, that is Z equal to R plus J into omega L minus 1 divided by omega C. Just substitute that, you will get the current equation. So if you want the magnitude of a current, that will be I equal to V divided by square root of R square plus omega L minus 1 divided by omega C whole square. So at last in your examination you need to write the So expression for impedance and expression for current. At last you write the both the equation and just explain the terms where Z stands for impedance, R stands for resistance, J is the operator, omega is the omega is the angular frequency, L is the inductor, C is the capacitor, and in the same way, so V is the I is the current. Explain all the terms in the word last expression, and this is all about your 10 marks derivation, that is expression for impedance and current in a LCR series circuit using a J operator. I hope this derivation is clear for you. So in next video we'll see the same concept but LCR in a parallel circuit. Thanks for watching. Keep subscribing.